Okay, let's dive in. Think about something really simple, like a knot in your shoelace. Now, what if I told you that studying these knots mathematically could actually help us understand things like quantum chaos?
Right. Or even black holes and, the fundamental limits of computation itself.
Exactly. It sounds, well, almost too strange to be true, doesn't it? But that's what we're exploring today, topological quantum field theories. TQFTs for short. Our goal here is to sort of reveal how these theories connect areas of physics that seem, on the surface, completely unrelated. They provide this really powerful, unexpected lens.
Yeah, and what's truly remarkable, and something our sources really emphasize, is how TQFTs are becoming critical. I mean, they started out pretty abstract, pure topology, studying shapes, spaces, that kind of thing.
Hmm.
But now, they're proving essential for understanding how information gets scrambled, how complexity grows in these incredibly complicated quantum systems.
Scrambled, like information getting lost, or just mixed up.
More like mixed up incredibly thoroughly. Think about chaos. Things look like a total mess, right? TQFTs help us see the underlying structure, the hidden order, even within that apparent disorder. We're going to explore how they give these surprising insights into what's actually important when systems seem chaotic.
And it's not just theoretical pondering, is it? I mean, my mind starts to boggle a bit when the sources explain how things like the Jones polynomial,
Ah, yes, the knot invariants.
right, these mathematical descriptions that give a knot its unique fingerprint, basically. They just pop out naturally from TQFTs.
Hmm.
And calculating them, it's incredibly hard computationally. Like, hashtag P hard. Hard.
Which is a serious class of difficulty. We're talking problems that even our best supercomputers would choke on.
Exactly. And that computational toughness, that difficulty in knot theory, it directly mirrors how circuit complexity grows in quantum systems.
Especially as you mentioned in black hole physics, it's a deep parallel.
It's like the difficulty of untangling a really messy knot is fundamentally similar to the challenge of decoding information scrambled by a black hole, the universe's ultimate information scramblers.
And if we bring in the holographic principle, the ADS-CFT correspondence.
Okay, the idea that gravity in higher dimensions is equivalent to quantum physics on a boundary, like a hologram.
Precisely that. You see this deep intersection between these topological models and quantum chaos emerge there. Chaotic quantum systems on that boundary map onto gravitational things happening in the bulk, the higher dimension.
So how do they track the chaos?
Well, physicists use these things called out-of-time ordered correlators.
OTOs.
OTOs. This sounds complex.
They are, but think of them as super-sensitive probes. They measure how fast information scrambles the quantum butterfly effect, basically. A tiny change now leads to huge differences later.
Okay.
And viewed from the gravity side, this scrambling process is fundamentally geometric. It's often modeled using tensor networks.
Tensor networks, like webs.
Kind of. Imagine a complex web of interconnected mathematical bits, and surprisingly, these webs often have an underlying topological structure themselves. This is where it gets really interesting for me. The sources talk about braided tensor categories and fusion rules coming out of TQFTs.
Leading to anyons.
Anyons. Right? These aren't everyday particles. They're quasi-particles whose paths can literally braid around each other.
Like dancing in 2D space.
Yeah. And they're not just key for building robust topological quantum computers, which is amazing in itself, but the sources say they can actually simulate chaotic dynamics too.
That's right. It's quite something.
So a theory rooted in knots helps us build quantum computers and understand chaos. How does their topological nature help with the computing part?
Well, that's a great question. The representations of the braid group, the mathematical description of how these anyons braid that pop out of TQFTs, they actually define operations in Hilbert space.
Hilbert space.
Yeah.
The quantum playground where states live.
Exactly. So these braiding operations can literally be used as universal quantum gates, the basic building blocks for quantum computation.
Ah, I see.
And because their function is tied to the topology, the overall shape of the braid, they're naturally resistant to local errors or jiggles.
Making them fault tolerant. That's the big dream for quantum computing, isn't it?
It is, and this ties back to chaos, too. These same mathematical structures, these representations, can mimic the exponentially sensitive behavior you see in chaotic systems. It mirrors something called the Loschmidt-Bekow, basically, how quickly a quantum system forgets where it started if you nudge it.
Wow.
So it's this incredibly powerful framework bridging quantum computing, fault tolerance, and the study of chaotic complexity.
Okay, so let's wrap this up. We've gone on quite a journey here, haven't we? From simple knots all the way to TQFTs, showing us the structure, even the limits of quantum chaos itself. It's clear they're much more than just a tool for classifying phases of matter. They seem to be this generative framework for understanding some really deep complexities in the universe.
Absolutely. It's genuinely fascinating. You have these very abstract mathematical ideas, TQFTs, providing incredibly concrete tools. Tools to diagnose, even simulate chaotic quantum behavior. It's like finding this hidden order in what looks like pure
Yeah,
randomness.
like the universe has these deep patterns, and TQFTs are letting us finally get a glimpse. So maybe a final thought for you, the listener, to mull over. If TQFTs can link knot theory to black holes, to the future of computation, what does that suggest about how unified physics might actually be underneath it all? And, how could digging deeper into these topological ideas reshape our very understanding of information itself?